And now I've written a program that actually does block swapping. Makes it a lot easier. It doesn't do the block swapping for me because I don't want to take human eyes off of this for error correction, but it makes it a lot easier so I don't have to go hunting through the files. So this particular program right here, go to load a script again, it basically opens the data block bytes report, CRC verified, from whichever read I think is the best. In this case, I took 3 reads of track 1R on this particular tape, the CTIX 5.1116 user. And this one was pretty useless. As you can see, well, I guess I deleted it because it was just taking up too much space and I needed space. This one, 1R 2 turns down, has relatively few errors. These are the only block errors that it had, which is down from, well, my first reads had like almost every block erroring out. So this is significantly better. And this one is second best, but some of the bad blocks here are not the same as the bad blocks here, meaning that they're good over here. So I just wrote this program to look at both of, to find, what does it do? It finds all of the, well, let's just go to it, all of the alternate blocks. When my data block bytes report, CRC verified or not, the alternate block exists. Well, the CRC verified is even better because the alternate block exists if there's any warnings saying that there's a problem with the data block. And the alternate block is what shows up right here, just like this. So you've seen this in my other previous videos if you've watched them. And I want to be able to replace this with the block that's supposed to go there. So this is my program's identifier of the block that failed, that had a problem, and that you need to replace it. So I'm just going through my my hex editor here to find these. And this program just looks, it goes through the source data block bytes report CRC verified, finds all of the alternate blocks, and assumes those are errors, and correctly so because they are, and then goes and, well, it always knows what the previous block number was. Now in this case we're using QIC24. So unlike the Kennedy format or other formats, the blocks are actually numbered. And QIC24 has superior block numbering over QIC11. QIC11 has block numbers 0 through 255, so that doesn't work nearly as well here. This really only works well with QIC24, and that's because every block number, at least on each track, and actually throughout the entire tape, is completely unique. Completely unique throughout the entire tape. So, what this does is it finds this alternate block, and it says, oh, well, this is on block sequential count 12679. 12679. And it looks for the previous block number, or at least it was always looking for it, so it remembers it, and then it opens up the subsequent other CRC verified data block bytes report files, and then looks for a match for, in this case, block number 0067BC, just like that, and it finds it right here, and so it basically adds any sections of a match where it finds the previous block, and shows me the block afterwards. And the idea is the block after this one is the one that has the error. Hopefully the block after this one does not. Now the reason that it tries to use the previous block number as a key value is because the sequential count for blocks might not be the same from one to the other. In other words, if a block is missing in the second read but it's not missing in the first read, the block sequence is going to be off. But since these blocks are numbered within the block themselves by the QIC24 format, that's actually very reliable. The QIC24 format, when the tape was written, had identified this block as 26556, and therefore the next block should be 26557. And so when it looks for another read in its data block by its report, CRC verified, it finds a text search match on block number 26556, but then also includes the block after that, which should be the next sequential block, 26557, and it is, which is absolutely wonderful. Now, in this case, it just so happens that the block sequential count of 12679 is matching the error on this one, but you cannot count on that. You absolutely cannot count on that, and that's why I've written this to be able to do this for me. Now, I don't want this to do an automatic find and replace, because I still want my human eyes to be able to look at this and to think and to say, is this a special circumstance? Because this is a very subjective process, and there can be matches where I actually don't want to use the data because something else went wrong. But I really want to have a hands-on look at this manual block replacement when I am reconstructing these files from QIC tape, just because I want to remove any errors possible. So let's see if we can use this to replace some errors. I jumped ahead a bit. We want to replace block 13573. And we're there, block 13573. The sequential block translates into block number 27410, one more than 27409. And it looks like this time we weren't quite so lucky. We didn't find a match there. So we'll keep going. We'll have to correct that using some other means. 13568. 13553. Where was I? Oh. Interesting. 13537. 13537. And 13568. So how did this find an error? '68 comes after 53. So there's 68. Well, this is interesting. How did I miss that? Oh, I'm glad I looked at that. This is actually finding corrections for errors that isn't even necessary. 27425, 27425, 27426. Great. This actually found a replacement for an error that was already corrected in the original tape. In a different section of my programs, you'll find that, let's see, which one of my programs does this? I believe it's the data block bytes. No, it's the data block counts. Yeah, the data blocks counter. And the way the QIC11 and QIC24 error correction works is if it writes a block with an error, it doesn't stop and go back and erase it. It rewrites the same block over again. And so the sequential numbering system actually backs up one or two, and it finds a replacement. And so I'll bet that if we go to the log that I have for that, which should be block count report. There we go. There we go. Alright, let's see what this has for us. We are looking at block number 13553. Block sequential count 13553. This is one that should have been corrected on its own, and let's see that it really was. And sure enough, the count went from 1355. Well, let's see. The count. Let's see. 27425, 27426, 27427. So 27425. This should have been 27426. I think that error was recognized when it was originally written. So block 27426 was then rewritten in sequential position 13.555. Excuse me, 13.554. It was 13.553 that errored out. 13.554 replaced it. And so my program correctly identified that. So we have a block sequence adjustment where, and this is the internal algorithm adding system that I used to figure this out. So roll back 1. So basically it recognized that if it had skipped over block sequential, excuse me, if it had skipped over block number 27426, and this was 27427, it would have kept this as a block error. But instead, it said, oh, let's replace this with this. So that error correction was actually already done by my program here, the data blocks counter. And that program was just made to emulate exactly what the QIC24 formatter board hardware does, and that is when it identifies a repeating block by its sequential block number. And I shouldn't be too confusing, because what I call sequential block number is different than what it calls sequential block number. If it finds a repeating block number, then it just replaces the previous one with the current one. And that's how that works. Hopefully that was clear. But that solves the mystery on why my program here found a replacement for an error that never made it into my final file, is because another program caught it ahead of time, which is always good to know. Okay, so 13568, we're safe to go on to 13568, and we got lucky. 13568, we're looking for block sequence 27439, or so we're looking for 27440, and look at this, 27440 was found in the next read, and the CRC is all okay, warnings are none, and so we are simply going to use this to replace the block. Very, very exciting, demonstrating that this actually works. And let's see if it fits in context. It's really hard to see here because we're clearly looking at, well, I think we're looking at binary machine language. And it certainly looks like the same kind of language, the same kind of gibberish. So it certainly looks like it belongs. And I have no reason to believe that it doesn't. So let's close this, and we'll look for one more. One more. See if we get lucky. 13743. And so that's the next one, 13743. Hey, we get lucky again. We're looking for block number 27614. And we found it. 27614 is good right here. So we get to use this to replace this block right here. And we are whittling these errors down. And interestingly, it looked like the first read wasn't that catastrophic. It was simply a CRC mismatch. So it must have misread one character or one data pulse somehow, but the whole thing still worked out, and my early programs didn't catch it. So it's working. It is working. We'll copy this, and we will paste it in here, just like that, and save. Okay, so that was enough of my demonstration. I'll keep on going there, so thank you. And so I just thought I would share that with all of you that are following this process. And thanks so much for your support on this.